Hello, today we're going to talk about Section 8.2, which begins our study of hypothesis testing. And I know hypothesis testing is kind of a hard concept to wrap your head around, but take all this in, and then the next video we'll go through example, how you find your null hypothesis and your alternative hypothesis and go through all your testing. So the key concept here in this section is to identify the null hypothesis and alternative hypothesis from a given claim. And we must know how to show those in symbolic form. Then we'll learn how to calculate the value of the test statistic given a claim and sample data. We'll also figure out how to choose the sampling distribution that's relevant to that problem. We will identify the p-value and also identify critical values. Then we need to learn how to state the conclusion about the claim. First, we need to state it as a reject or accept the null hypothesis. And then we also need to do this in a simple and non-technical term so that other people can understand what we really did with that test. So a hypothesis is a claim or statement about a property of a population, and we can do that using a proportion, which is, of course, we know is a percent. We could do that about a mean, or we could also do that about a standard deviation. Then once we make that hypothesis, we would perform a hypothesis test, and that is a procedure for testing about the claim, about that particular population. We really already know these next two things. A rare event rule for inferential statistics is given that the probability of a particular observed event is exceptionally small. We conclude that the assumption is probably not correct. And we've done that before. We've looked at things and said, oh, that's not going to happen because it's unusual were the terms that we used. Well, note that while we're conducting the study, we want to use a hypothesis test to support that claim, and the claim must be worded so that it becomes the alternative hypothesis. So our null hypothesis is going to be denoted by H naught, that little O down at the bottom like a subscript. And that's a statement that the value of a proportion parameter, and again, it could be a proportion, a mean, or a standard deviation, and this is the key. The key to identifying which is the null hypothesis is that it is equal to some claimed value. So it could be less than or equal to, greater than or equal to, or just plain equal to, but that's going to be our clue as to which is going to become our null hypothesis. Then we test the null hypothesis directly in the sense that we assume that it is true, and then we will either reject the null hypothesis or fail to reject the null hypothesis. Those are your only two outcomes that you have. The alternative hypothesis is going to be H sub 1 or H sub A, and it is going to differ from the null hypothesis in that it will only have the symbol less than or greater than or simply not equal to. So again, that's the key in deciding which is the null and which is the alternative hypothesis. So our steps here in identifying them, we're going to identify the specific claim as hypothesis to be tested and put into the symbolic form. We're going to give the symbolic form and know what must be true when the original claim is false. And I know that's a little opposite of what you think, but let's keep on going with it and it will become clearer. Of the two symbolic expressions, again, we have to be able to recognize which is which. So the alternative hypothesis has that symbol of greater than or less than or equal to. The null hypothesis has the one that has the equal sign. And again, it could be greater than or equal to, less than or equal to, or just plain equal to. So here's an example. We're going to assume that in that XSort method of gender selection, and that makes a claim then the claim is that it makes girls more likely. So we observe in our sample that 58 girls were produced in 100 babies. So we needed to write the hypothesis to test the claim and the XOR method. The proportion of girls is greater than 50% that occurs without treatment. So clearly we need to write this part right here. That becomes our claim. The proportion of girls is greater than 50%. So all we would write right now would be this statement in symbolic form. Well, if I'm writing that statement in symbolic form, that gives it dead away that, well, that's going to become my alternative hypothesis, because I know for a fact that my null hypothesis must be where I have the equal sign. There was no equal in this one. If this had had greater than or equal to, then simply we would rewrite the null hypothesis to say P is equal to. So our next step is selecting the significance level, and that is how small of an area that I would be considering what we think of as critical areas or unusual areas. So we're going to call that alpha, and that's going to be based on the seriousness of a type 1 error. So if we make a small consequence, if there's small consequences, I mean like nobody's going to die or anything, or you know, a child that has something isn't going to miss out on treatment, um, you know, something like that, we would have to have a very, very small significance level. But something that's not as critical, we could have values of maybe 0.05 and maybe even 0.01. Those are very, very common significance levels. So again, that significant level is denoted by alpha. It's the probability that the statistic will fall in the critical region, and when the null hypothesis is actually true. So we want to make sure that what we get is correct. So if we put out to the ends these little critical areas, and if it falls in the critical area, we would be making this mistake of rejecting the null hypothesis when it's true. So we want to make that area small. The bigger the ramifications of making that error, the smaller we need to make alpha. This is the same alpha that we talked about in 7.2. The common choices for alpha again are 0.05, 0.01, and sometimes we use 0.10, and of course that would give us, as before, a 90% confidence interval. So then we need to identify the test statistic, and it all depends on what we're testing around. So the ones that we're going to be worried about in this course are going to be the population proportion, the mean, when I do not know my standard deviation and it's normally distributed, or I have n is greater than 30, the mean, which would be the normal z, when our standard deviation is known and normally distributed population, and n is greater than 30. So two cases, we're going to use our normal Z sampling distribution, and we've been working with that all semester. But then if it's not, we're going to use the T, and we saw T already. So that's how we're going to determine which test statistic we're going to use for that distribution. So the test statistic is the value used in making the decision about the null hypothesis. We want to make sure whatever our sample is, whatever it's about, we are converting it to that sample statistic, the Z or the T. Step 6, we're going to find that statistic and find either the p-value or the critical value. So we're going to transform everything to the standardized score called the test statistic, Z or T. From that, we'll be able to find our p-value or our critical value. So our p-value is really the area under the curve, and the critical value is that T or Z, which separates the what we think of in the past as usual or unusual. So here we go. Let's again consider that claim about the XORT method, that it would increase the likelihood of having a baby girl. Well, as we said earlier, the results from a test that involved 100 people produced 58 girls and 42 boys. So we're going to use that claim and the preliminary results to calculate the value of the test statistic. We're going to find out the format of the test statistic so that the normal distribution is used to approximate the binomial distribution. So here's our example, and if you would remember, we had our null hypothesis where the chance or proportion is equal to 0.5, half a chance. It's either 50% girl, 50% boy. And because the claim was that, if you'll remember, the XORT method increases the likelihood of having a baby girl. That's our claim. So that is our alternative hypothesis. So we work on the assumption that the null hypothesis is true with a p of 0.05. The sample proportion, p hat, we've done p hat before back in 7.2, 7.3. P hat is we got 58 out of 100 or 0.58. So that's our sample, p hat. So we're going to convert that test statistic, and because this is a normal distribution, etc., we're going to use that Z statistic, and we're testing around a proportion. So we have p hat minus p, and then we're going to divide that by the square root of p times q. Remember what p times p and q is, all divided by n. And notice it's p and q, it's not p hat and q hat here. So we're going to take p hat 0.058 and subtract the proportion that we're saying that's in our claim of the null hypothesis, 0.5. We're going to divide that by the square root of, and p hat, or I'm sorry, not p hat, but p and q, because this is p, so this is still p. And of course, q is 1 minus p. And we do that multiplication, and of course is the number on our sample, which was 100, and we come out that our Z is at 1.60. Well, we already know that a Z of 1.60 is not unusual. At first glance, 58 girls does not seem to support the claim that the XORT method increases the likelihood of having a girl by more than 50%, because it's really not that high. It's really in the usual category. So there are different types of hypothesis tests. There are two-tailed, which means that, and I have a normal curve. Let's draw a normal curve so you can see what we mean here. A two-tailed, I would have a small area on this end and a small area on that end. That's a two-tailed. We could have a left-hand tailed and a right-hand tailed. This would be a left-hand tail, and this would be the right-tailed. So determinations of the p-value and critical values are affected by whether the critical value is in two tails, the left tail or the right tail. That becomes important to correctly characterize a hypothesis test, whether it's two-tailed, left-tailed, or right-tailed. Here's a two-tailed test. When you have that two-tailed test, you do, like we said, have area on both sides where we will reject the null hypothesis. All the area inside, what we usually think of as usual, would be the fail to reject the null hypothesis. And this again happens, and we use this when we have the situation that the null hypothesis is equal, because the null hypothesis is always equal, but the alternative hypothesis is not equal to. It doesn't say greater than, it doesn't say less than, it just says or not. It says not equal to. So that would be a two-tailed test. A left-tailed test happens when the alternative hypothesis says it's less than, and of course less would be down this way. So we're checking for when it's in this critical area. This area would be where we reject the null hypothesis. And much like that, when we have the alternative hypothesis, and that alternative hypothesis has the greater than sign, that means greater than, bigger than, we would have just this one tail where we would reject the null hypothesis. So our p-value or probability value, you cannot get that confused with the p being a proportion or p hat being the proportion of a sample. So our p-value is the probability of getting a value of the test statistic, whether it's a z or a t, at least extreme as one of the sample data. So our critical region to the left, the p-value to the left of the test statistic, critical value to the right, of course, is the right, and the critical value in two tails is the p-value is twice the area of the tail beyond the statistic. The null hypothesis is rejected if the p-value is very small, and usually we will look at 0.05, sometimes we go to 0.01. So here's an example. We go back to the same example about the XOR methods. We calculated out our Z. We found our Z to be 1.68. And if we went to our table or we went to our calculator and we found the area, now be careful, we're finding the area to the what? To the right of the Z, and we do that, the p-value, and of course the p-value is the probability, which of course is the area under the curve, comes out to be 0.0548. Much like before, when we looked at our z-score earlier, we said we already know that that z-score is usual rather than unusual. In other words, it's not going to be out in that far tail. And when we looked at that, found the p-value being 0.0548, and we know we're testing at a p value of 0.05. Well, 0.548 is bigger than 0.05. So it fails that test as well. And of course, regardless if you're using the actual critical value of z is equal to 1.6 or you're using the p-value, you get the same result. You fail to reject. That hypothesis, that null hypothesis. And let's just draw it out just to make sure you're understanding what's happening here. So we're going to draw a normal curve. We've already said this is going to be to the right only. We did our calculation. When we did our calculation, we found that our z was 1.60. When we used our table, or used our technology, we found this area as being 0.0548. Knowing that, we know that it has failed because this is larger than my critical. So let's get a different color, which would be our critical. Our critical area would be this area, and we are beyond that area. This little area here, 0.05. If it fell in here, we would reject. Here, do not reject. That's how we test about the claim. So here's our procedure for finding our p-values. So we have to decide if it's a two-tailed test, a left-tailed test, a right-tailed test. And we already know that right-tailed test is going to be greater than, left-tailed is going to be less than, and a two-tailed is going to be equal. And with the alternative, sorry, not equal. So if it is a two-tailed test, we find that the p-value is twice the area to the left. The p-value is twice the area to the right. If it's a right tail test, it is the area to the right. Left tail is left area to the left. So that critical region or rejection region is the set of all values beyond that critical value. Remember, the critical value is the area that separates the critical region, and that's where we reject the null hypothesis. The critical values depend on the nature of the hypothesis. And again, we have to worry about the significance level. So here's an example. Again, here it's a better drawing that I could do. The XOR birth hypothesis test, the critical value and region for an alpha. The alpha that I'm testing is 0.05. For 0.05. And we already know this from section 7.2. My critical C for that is 1.645. The area, because that's my significance, is alpha is equal to 0.05. When I did my sample, I came out with 58 births out of 100, giving me p-hat of 0.58. We then looked at 0.58 and found my Z to be 1.6. So if you can see Z being 1.6 lands in the blue area, anything in the red area would mean that I would reject. But because it lands in the blue area, we will fail to reject. And again, just a reminder, do not confuse the p-value with the proportion p. Remember, proportion p is going to be my population proportion. My p-value is really the level at which I'm testing my claim. So the next step, I know they're long steps. Step 7 is to make that decision. And again, the things that we're going to learn to use are our p-value method, where the p-value that we find is less than or equal to alpha, or the p-value is greater than alpha. We would reject, and if it was greater than alpha, we'd fail to reject. Just the ones that we did before, we had the p-value came out to be 0.0548, 548, and because it is higher than 0.05 is higher than this number, we fail to reject the alternative or the null hypothesis in this particular example we've been using. So again, the critical value method, we're going to find our regions, we're going to find that test statistic, whether it's a T or a Z, and find out where it runs, compare it to what happened in our method, and of course this one was a T of 1.6, the critical value is 1.645, so again we failed to reject. and that goes through exactly what I just said, though Z of 1.6 did not fall in the rejection region. You can use either method to check whether something falls in the critical reading where you would reject. So lastly, or the step 8 is to restate the decision using simple and non-technical terms. Remember, we are not testing that it's true. We are testing to see if we can reject the null hypothesis. And you have to keep that in mind. And for this particular example, we were going to say that there was not, well, I meant that be a highlighter, sorry about that. There was not sufficient evidence to support the claim that excerpt method is effective in increasing the probability of a baby girl will be born. Because why? We found that 0.58 was still in that usual range. It is not unusual. So we don't have anything to support that it would be unusual, and that because of this test. Okay, here's a little chart helping you to word your final conclusion. It all comes and stems off of the original claim. So always, 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 the first step is look at what the problem says, the original claim. In this case, it said it would increase the proportion or probability of getting girls. Increase it, meaning, of course, it is greater than. In that case, it did not have equality. It did not have equality in our original claim. So we came down this way. Do we reject? Yes, the sample data support the claim. If we fail to reject, which we did, there is not sufficient sample evidence to support the claim. If your original claim contains equality, when we reject, there is sufficient evidence to warrant rejection of the claim that, and if we fail to reject, it is not sufficient evidence to warrant the rejection of the claim. Never ever conclude a hypothesis test with a statement of reject or fail to reject. Always make sense of the conclusion with a statement that uses simple, non-technical wording that addresses the original claim. In other words, you want the general public to be able to understand what that meant rather than just saying reject the null or not or fail to reject, because they don't know what that means. You didn't know what that means until you're learning all this. Sometimes people say accept, but in our study, we're going to say fail to reject. Then we got to talk about errors. And we kind of mentioned errors a few minutes ago, but there's a type 1 error and a type 2 error. Type 1 error is the mistake of rejecting the null hypothesis, but the null hypothesis is really true. We use the symbol A or alpha to represent that probability. A type 2 error is the opposite. It is the mistake of failing to reject it when we should have. So that is B or beta, and it's used to represent the probability of a type 2 error. So here's a nice little chart that helps you make and understand what a type error is. And again, type 1 error occurs when we decide to reject. Type 1 is when we reject. The error is that the null hypothesis is true. It would be correct if the null hypothesis would be false because we did reject it. We fail to reject. When we fail to reject and we should have, that's a type 2 error. So here we are with back to our same example. Here's, remember, our alternative hypothesis, our null hypothesis, and we want to identify a type 1 error and a type 2 error. So remembering that a type 1 error is the mistake of rejecting a true null hypothesis. So we conclude, in this case, the probability of having a girl is greater than 50%, when in reality it is not. It didn't reach out there to those critical areas, those tails. A type 2 error is the mistake of failing to reject the null hypothesis when it's false. And there's been no evidence in this case to conclude the probability that having a girl is greater than 50%. In reality, the probability is greater than 50%. So these are ways that we can control type 1 and type 2 errors when we set up our test. If we have a fixed alpha, if we increase the sample size n, we'll cause alpha A decrease in B for beta. If we have a fixed sample size, a decrease in alpha will cause an increase in beta. Conversely is also true. To decrease both A and B, increase the sample size. And that's it for section 8.2. I will come back with a second video that will begin you in your process of examples on how to identify the null hypothesis, alternative hypothesis, determine what your test statistics are, look for your critical values, whether you're going to be using your test statistic and or your p-value method, and then concluding whether you reject, fail to reject, and summarize your statement.